Okay, colligative properties. What do you guys want to put up here for a response to what are colligative properties? Agree with that? Changing the properties of pure liquid when a solute is added? Something like that? And how do the colligative properties affect the liquid state of a substance?
How do you say last longer?
No, I like what you were going to say initially. What were you going to say?
Bigger?
That's it. It just makes it bigger, right? It's a liquid over a larger range. So larger range for liquid state. When a salt is added to water, why does the boiling point elevate?
Is it because the bond between salts?
Do you want to use the word bond or do you want to use something else?
Is it intermolecular bond?
Do you want to use one? There you go. Yeah. Don't use the word bond, but I would say that the intermolecular forces of water to
Sodium is stronger than water.
an ion is greater than water to water. So there is definitely an attractive force between two water molecules, but water molecule being attracted to an ion is going to have a greater force. So to get that water to boil, what do you need to do to its temperature?
Raise it higher.
Why is increasing the temperature going to allow this thing to continue to boil or to start boiling? Okay, so I'm going to increase temp, and that's going to increase the energy, and that's going to increase the speed. So it'll be moving faster. So it'll be able to break those bonds. So really it's just about speed. How fast does the rocket need to be moving when they want to launch somebody off of the moon in relationship to trying to launch somebody off of the Earth? Not as fast, right? I mean, the lunar module's rocket is tiny compared to the rockets that they needed to use to get it off the Earth.
If they needed the same amount of fuel, then I don't think it'd be able to leave.
What? That was a little, it was probably a little like heart-wrenching for Armstrong and Aldridge, right? Like, let's hope that the physicists were right about that whole 1/6 the size thing. Otherwise, we're going to go right back down and hang out for a while. 5 or 6 days, and that's about it. When salt is added to water, why does the freezing temperature become depressed?
Because it's sad when it's cold.
Yeah, that's it. It's salty.
The water to salt bonds are stronger than water to water.
Okay, so the answer is almost exactly the same as it was for the last one. All of this that we have written, all of this stuff about the intermolecular force of water to ion is greater than water to water, that goes down here. That is exactly the same. But the difference in this case is, instead of increasing the speed to get the water to boil more, what ends up happening is the fact that the intermolecular forces are greater for ion to water disrupts the crystal matrix structure of the ice. So the solid's crystal matrix structure is destroyed.
Like it's unable to form, or it's
How about it's disrupted? They are no longer able to align correctly. So to get something to be a solid, bless you, you have to actually have everything lined up, and this messes all the lines up. So the hydrogens and the oxygens are no longer hydrogen bonding to each other because they're hydrogen bonding to the ions, and so now I don't have this nice even structure. All right, so this next question here, what are the units that I'm looking for this answer? I'm looking for moles per liter because I asked for concentration and all I see up here are moles per liter. So can you describe what we have? Yeah, I've got a solution and I've got another solution, and I dump all of that into a big container, and then I add some extra water to it. So what's going to happen to the concentration overall? It's going to drop dramatically because I threw a whole bunch of water in. So I've got a concentrated stuff and I got another concentrated stuff. I dump them together, so their concentrations are in some way going to average out depending on their concentrations and volumes. And then I throw a bunch of water in and dilute the whole thing down. All right? So what I need to calculate moles per liter are what? Moles and liters. So I need to know how many moles I have, and I need to know how many liters I have. How many liters do I have excess water am I throwing in? I'm going to throw in 2 extra liters. Okay, and then I also have 400 milliliters of one solution, and I have 250 milliliters of another solution. So completely, I have how much solution? 2.65 liters. What? Okay. I am not minding. But what I need are the total number of moles. So that's the total volume. So what's the total number of moles? How many moles were in the water that I added? 0 moles. All right, so that doesn't matter. How many moles are in this? And how many moles are in that? Okay, I need to do a little calculation to determine that. So for the first one, I've got 0.13 moles per liter, and I've got, let's get 2. How much? 250 milliliters, so 0.25 liters. And then for the next one, I've got 1.75 moles per liter, and I've got 0.4 liters. Okay. So what does that work out to be? 1.3 times 0.25, 0.325 mole, and I've got 1.75 times 0.4 at 0.7. 1.025 mole. So that's the total number of moles of NaCl that I have in here, so I'll put 1.025 here, and then that'll be moles per liter. And so I've got 1.025 divided by 2.65. I got 3.87, and it looks like I have, it's gonna only have 1 sig fig, lame. All right, 0.4 mole per liter.
Only 1 sig fig?
Right here, there's only 1 sig fig in 400. Yeah, I know. Are we okay with that? Do we see what we did here? I mean, you have to think about this being 3 different liquids, and that the liquids, some of them have stuff in it and some of them don't. But in the end, all I care about is what's the total volume and what's the total amount of stuff inside there. So if you can just break it up into the pieces and then add the pieces together, then you can do the calculation. So the math wasn't really hard, it's just sort of like we had to think about what it was that we were doing with this. Any questions about this one?
The first part, like, correctly, but then when I got the total amount of the moles and liters, I did the solution, I think, equation because you're diluting it with the extra water. Does that make sense? Like, I found the amount of moles
Yeah.
in the...
And then you did the dilution equation?
Yeah, because you were diluting it with extra water. I have no idea what my answer was, quite honestly, to know if it was correct or not. Probably not, but...
I do, in a second. Nope. When you determined that you had so you did the 0.325 moles, correct? And you did the 0.7 moles, and then you added those up, and then you said that was moles per liter. So that liter materialized out of nowhere. I mean, you literally have 0.325 moles plus 0.7 moles, and down here it says 1.025 moles per liter. That's just, well, you just added moles and moles together, and you just you went miles, and then you changed it to miles per hour just for the heck of it.
Okay.
So with the problem like this, that's the first question they ask is, what unit are we looking for? And it's moles per liter. So if you know the total number of moles, the definition for molarity is what? No, that's a quick definition, but that's not the definition. It's moles of solute, and in this case, what's the solute? So table salt. So if I figure out the total number of moles of the solute, which is this value down here, and then what's the denominator? Liters of solution. And the liters of solution are the 2 liters and the 400 milliliters and the 250. So, yeah. There are instances where you might be, I don't know where any of you are going to be in healthcare are going to be. You might never actually touch this stuff, or you might go to some very rural healthcare facility, and this is you're the farm tech, and this is how you would have to mix these things up. So you need to, it could be in moles per liter, but it would probably be in percentages. Regardless, it doesn't really matter. If this was a 2% solution and a 6% solution, and then certain amounts of those, and then you diluted it with another 30 milliliters of water, you still need to know what that percentage is. So this isn't something that is just for the heck of it, and I'm seeing if you can figure it out. You could see a problem that looks like this.
I have a question about
Yeah.
I'll wait because I think it's going to be applicable later, and then I'll ask it.
Okay.
Okay.
How about this one? Which is a better electrolyte? When you see this question here, the first thing you should ask yourself is, are they dissolvable? Are they soluble? If they're not soluble, then one of them is a non-electrolyte, and then that answers the question for you no matter what. So are these both soluble? Yeah, there's a chloride up there that's not with a mercury 1 or a silver or a lead, and then there's a magnesium sulfate, and sulfates are soluble as long as they're not with barium or calcium, and so they'll both dissolve. So great. Okay, so now when I dissolve them, what are the benefits of one of them?
The magnesium sulfate.
This 2 pieces, this 3 pieces. So who's a better electrolyte? The calcium chloride.
I was thinking the opposite because it has a +2 or a -2, so
So?
it has a stronger force.
Okay.
So that doesn't make it stronger?
How many pieces are there?
Oh.
Well, you want to say that this is a +2 and that's a -2, but that's a +2 and this is a -1 and a -1.
Right.
So the charges are equal.
I was thinking though that a +2 by itself is, or a -2 by itself is better than 2 -1s.
What would you rather have, like one really strong helper to move, or 2 good movers?
2 good movers.
2 good movers, right? That's the sort of, and when we're talking about electrolytes, what are we talking about?
What it breaks into.
No,
Electrolyte.
no.
What do you?
That term electrolyte is referring to what?
Electricity.
Yeah, electricity. So when we're talking electricity, we're talking about what? Electrons. And in terms of electrolytes, we put up that nerve ending thing. What I need is something to move the electron from one nerve to the other nerve across that junction. The more things that are able to move, it doesn't matter if it's a +2 or a -2 or the charge, is it charged? Yes, then I've got more things to move it. I mean, if I'm only moving an electron, if I'm only moving one small thing, and it's basically the smallest thing in the universe, right? Do I care that the thing that's carrying it is way bigger than it needs to be, or big enough to move it?
Big enough.
So you're gonna put a TV inside of a 24-foot Ryder truck, or you're gonna put a TV in the side of a, I don't know, what's a small car? A VW Bug. It still gets moved, right? Doesn't really matter. So if I've got 2 VW Bugs and I need to move TVs to 2 different places, then yeah, I'd rather have 2 VW Bugs instead of a big truck.
So what if you had if you had something, let's say potassium chloride? I don't know if that exists.
So potassium chloride,
Would be,
2 pieces. So this thing here and this thing here, they'd be about the same. As far as colligative properties, it would be different. But as far as being an electrolyte, they'd be the same.
okay.
So if I put magnesium sulfate in water, would it do a better job of increasing the boiling point over potassium chloride? Yes,
Because of the charge?
because of the charges, for sure.
Okay, so colligative properties, the charge can matter, but for electrolyte purposes,
It doesn't matter. But the other thing about the colligative property things is we usually think about it being in terms of, I put a pound of this on there, right? I go to the store and I buy a pound, or like a 3-pound bag. Well, if I buy a 3-pound bag of this and a 3-pound bag of KCl, well, which one is giving me more actual particles? That one, because it's lighter. So if I'm talking about moles, I mean, if I go to the grocery store and I'm buying 3 moles, which would never say, and 3 moles of that, then yes, this one would be better because it's the same number of particles. But if I'm purely doing it off of mass, I'm going to get so many more particles out of this that's actually going to end up being better because this is more than twice the mass.
Okay.
So there's lots of things to think about, but just as far as it being electrolyte, being able to transport electrons, this one's going to have 3 pieces. Okay, percent solution. So I've got grams and I've got milliliters and I want percent. So 35 grams divided by 400 milliliters times 100, and what does that equal? 8? 8.75%, so 9%, since I only have 1 sig fig. I will say I guarantee that on the NCLEX exam, it'll say 8.75, and that'll be answer A. And answer D will be 9. Yeah. Volume of 454 milliliters of beer with 3.5% alcohol. So in this case, I've got 3.5%. I've got some amount of solution, solute solution, and I've got 454 milliliters down here, and then this is times 100. So if I calculate this out, I get X is equal to 3.5 times 454 divided by 100, and I think this is 16 or 17?
15.89 is what I got.
Great, 16 milliliters, 2 sig figs. Does anybody know what beer that is?
Budweiser.
Beer sold in Utah.
It is the most sold beer on the planet.
Coors Light.
Coors.
Wow, so far off.
The most sold beer on the planet?
On the planet,
Bud Light.
Guinness.
Guinness. It's
On
Guinness.
the planet, not.
Planet, I said planet. Guinness, yep.
Guinness.
Why do
Revolves around.
Irish guys think that they can live off of Guinness?
Because it's delicious.
It's a meal in a can. Why is a porter called a porter? Does anybody know?
There's a maker near airports.
Nope. Good guess though. Nope. Because porters, and what does a porter do as far as a job?
Oh, transport stuff.
Pick stuff up, carries things. At that time, it was like carry big, heavy things. So what did they have during their break? A porter. Why did they have a porter?
Meal liquor.
It was a beer in a can. It was bread in a can, is what it basically works out to be. So a Guinness is a bunch of protein and a bunch of carbohydrates, and powers you through your next whatever. I mean, I worked at Kells for like 3 years, and I saw some Irish guys binging during like soccer World Cup stuff, like 4 straight days. Every once in a while, they'll have a boat of chowder, but really, they're like 12 or 13 glasses of Guinness in a day. Go home, go to sleep for like 3 hours, and then come back and watch more games. Yeah, they can pull it off. Yeah.
A percent carries, this is obvious, no units. So when you,
The unit thing is a little screwy with percentages. You have to know what it is that you're looking at, and then just think about if the unit is going to be correct or not.
okay.
For this last question on this page, the two equations that we used were what? Uh-huh.
Mass of solute over solution volume times 100 equals percent.
We use those two. Mass to volume and volume to volume, percent solutions. So when you're looking at something and it's giving you a value as far as its concentration and percentage, it's supposed to say this after it. MV, MM, VV, one of those. And then that's going to tell you if the, how they actually did the measuring with that. And which one of those is the most accurate? MM. Why?
Because the mass doesn't change by temperature.
Okay, the mass doesn't change with temperature, but more importantly, if I spent a lot of money on the scale, I could get many, many decimal places, as opposed to trying to read a graduated cylinder or a volumetric flask. I mean, how many times did you guys fill those vol flasks and then I sent you back to put like another drop in? So it's not as easy as it's just on that line, but it's really easy when I just set the thing on a scale and it says, 400.00. I mean, I'm done. That's it. But that balance is going to be very expensive as opposed to a $30 volumetric flask that takes 2 seconds to fill up. Yeah. Okay. There's just a little bit of trickiness to this one, but not a lot. So I've got a change in the temperature of the freezing point, and the equation that we said for that is NMKF. So let's start off with that N. What's the N value for this substance? 3, right? Because magnesium chloride is MgCl3 or MgCl2. So I've got a 3 there, and then I gave you the concentration at 2.5 molar, and then the Kf is 1.86 degrees C per molar, so the molarity unit cancels out. And then I just have degrees C for my unit, and do you have a number for that? Anybody? 13.95. Okay, so now here's the tricky part. I asked you what the temperature was, the new temperature freezing point was in Fahrenheit. So you're going to have to do a calculation. But before you do the calculation, you should actually figure out what the temperature is in Celsius, because it'll make it easier. What is the freezing point in Celsius
0.
of this solution?
1.86.
What does this thing mean? In the change in the temperature of the freezing. Negative 13.95. That's really important that you realize that it's negative. This is a freezing point problem, right? What does the freezing point always do when you have the solute? Goes down. So whatever value I get out of this, since this is a change in the temperature, and I know the temperature freezing point is 0, then it becomes simple for the Celsius ones. I just put a negative sign in front of it. Okay, so now that I know what this freezing point is of this solution in degrees Celsius, then I can just use the equation to calculate out what the freezing point is going to be in Fahrenheit. If I do it this way, it's a lot easier than figuring out what the change is and then thinking about the change from 32 and knowing what the value. So my suggestion is just figure out what its new temperature is in Celsius, and it's easy because I just put a negative sign in front of it. What if we were doing the boiling point one? What would you do? Add 100 to it, and then now you have the new boiling point. Okay, so then if I multiply this by 9/5, and then I add 32 to it. Is that right?
Yeah.
Okay. Negative 13.95 times 9 divided by 5 plus 32. And I get 6.89 degrees Fahrenheit. Are we okay with that? Does that number make sense?
Yeah.
Because freezing 32, so it's not quite 0, and yeah. Do you remember what temperatures Celsius and Fahrenheit equaled each other at? It was just an obscure number.
-40.
And -40, they're the same. So, they're not, it's not -40, but it's getting down there.